Hey everyone, so the next unit that we get into is another important one when we are looking at analyzing the topic of mechanics. And in case you don't remember, hopefully you do, but in case you don't, mechanics is the study of motion, and we've already looked at a couple of different aspects of mechanics. So the first aspect that we looked at was called kinematics. And we said the kinematics starts answering questions for us like where and what and what next and when. And that's when we introduced our topics of displacement, velocity, acceleration, and time, and how all of those things come together, how they affect one another, Suvat equations, and whatnot. We just finished up a unit dealing with dynamics. And for dynamics, we start answering the how, or the why question. And we learned that the answer to that question is force. And force causes acceleration, and we looked at the relationship between force and mass, and how much acceleration occurs, etc., etc. So today, we're going to get started on this aspect of energy. Now, energy can be tricky because it's another one of those things that if I asked you to define energy, you probably could. But when we talk about it in a physics sense, it has a very specific definition. And you'll see here that I have this little subheading here, energy is how things get done. Well, that kind of sounds a lot like force. And what we'll find out is that they are very similar in a way, that they analyze very similar situations, but what we analyze and how we analyze that situation does change. So we'll start with a definition. It says here, energy, the ability to cause a change in the matter or the environment. A change in matter or the environment. And this word, right, cause a change, change is represented by acceleration. So we're dealing with things changing, and that's why there are a lot of similarities between our energy concepts and our forces concept, right? We're not going to look at different problems. Some of the problems we do in this unit are going to be very similar to problems we've done in the past. We're just analyzing them a different way. So energy is the ability to cause change. How that change happens can be caused in a lot of different ways. There are several different types of energy out there in the universe. They all can cause change. While all of them can cause change, all of them are scalar quantities. They don't have direction, just magnitude. So when we look at analyzing energy, we look at, okay, how much change can it cause? Here is a table that summarizes energy, and in your book, page 62 has a more detailed list. But for the most part, in this unit, we are going to stay over here on this side of this graphic, and we're going to talk about mechanical energy. Mechanical energy, mechanics, right, deals with motion. So we're dealing with basically three types of energy here. Kinetic, gravitational potential, and elastic potential. I'm assuming you're familiar at least with kinetic and gravitational potential, maybe not so much elastic. But whether energy is mechanical or non-mechanical, that change idea still is in effect. So let's start analyzing these a little bit more closely and start defining some things, or at least refresh your memory. So first, we're going to start with kinetic energy. And I think way back in 5th grade or wherever, or maybe even 2nd grade, when you start learning about energy concepts, you learn that kinetic energy is defined as energy of motion. By virtue of the fact that something is moving, it has the ability to move or change other stuff. The amount of change that can occur, it depends on two factors. First depends on the mass of the object, but it also depends on how fast it's going. Now you'll notice here I have a couple of details written. First, V is represented in this equation, but V represents the magnitude of the velocity. Remember, energy is scalar. It doesn't have a direction. So it doesn't matter whether you have a positive velocity or a negative velocity. All that really matters is the magnitude of the velocity, or the speed. And mathematically, if you take a look at the formula that summarizes the effect of mass and velocity, where the kinetic energy is equal to 1/2 mv squared, even if you tried to put a negative number in there anyway, when you square velocity, it would come out positive. So here, again, no positive or negative on kinetic energy. But the amount of damage an object can do because of its motion depends on the two factors, mass and velocity. Mathematically, you see here that we are squaring velocity in that formula. That means that changing the velocity of an object will have a greater effect on its kinetic energy than changing the mass of the object. It says down here the SI unit for energy is a joule. So let's take a look at this formula. Okay, a joule is a derived unit. So if we take a look at kinetic energy is equal to 1/2 mv squared, 1/2 doesn't have a unit, so we don't have to worry about that. Mass is measured in kilograms. Velocity is measured in meters per second, but we're squaring that quantity. So when that all comes out, we end up with kilograms times meters squared over seconds squared, or if you wanted IB it, kilograms times meters squared times, kilograms times meters squared times seconds to the -2. All those together are represented by the capital letter J for unit joules, named after James Joule, who did a lot of work with heat engines and things like that back in the 1800s. So kinetic energy is measured in joules. It's this combination of units. But there are other ways that we can cause change. Or, if the conditions are right, we might cause change. And that brings us into potential energy. While kinetic energy is energy of motion, potential energy can be described as energy of position or condition. The object has the ability to move or change matter due to its position or where it's located relative to other stuff. And that's kind of broad because the other stuff that it can be relative to results in different kinds of energy. So the condition of the object means that it could potentially move or change matter. Not that it is currently moving or changing matter, but it could potentially. The first type of potential energy that we start with is gravitational potential energy. So if potential energy in general is energy of position, gravitational potential energy is going to be position relative to some source of gravity. Usually that source of gravity that we consider is the Earth, because the vast majority of our experience occurs here. But any object that has gravity, which we'll find out later is any object, can supply gravitational potential energy. If we go over here to the picture, right, we see this girl, she's lifting a crate up high onto this ledge, and then slides it across the ledge, drops it on this coconut in order to break it open. Why you would go through all that work to open up a coconut, I'm not sure, but whatever. But the important thing being is that that crate, when it was on the ground, did not have the ability to cause change in the coconut. But when we lifted it, because of the change in its position, it now has the ability to potentially damage the coconuts. We push it off the ledge, we turn potential into kinetic, and we'll talk a lot more about that in a couple days. And that kinetic then breaks the coconut open. So, what determines how much change an object could potentially do relative to its position on Earth? Well, there are three factors that go into it. I guess I should say more generally, relative to its position to a source of gravity. Three factors. Potential energy is equal to mgh, and I know I wrote it this way because I forgot to change it. So here, mgh. The mass of the object that we are changing the position of. In the case of the picture we just saw, that would be the crate. How big that object is could cause more damage or less damage than a lighter or heavier object. How high do we lift it up? The actual position will also play a role. But then the third factor is the effect of gravity, or the acceleration of gravity caused at that location. We know that here on Earth, that value is 9.81, but if we went to the moon, even if we had the same crate lifted the same height off the ground, it wouldn't cause as much change. Why? Because the effect of gravity isn't as strong on the moon. Gravity's effect is only about 1.6 meters per second squared. That would greatly reduce the amount of damage or the amount of change that that box could cause because of its position. So three factors: M, G, H, the mass of the object, the effect of gravity at that location, and how high above the ground that we make it. The last type of potential energy that we want to talk about is elastic potential energy. Again, it's potential energy, so it deals with condition or location. And the condition that we're talking about here is compressing or stretching an object. Because of the atomic nature of an object, protons, electrons, etc., if we stretch or deform that object in some way, it will try as much as it can to go back to the original condition or the original position. If you want to think of it like inertia, you can. Things don't want to change what shape they are. And if we force them to change, they will attempt to go back to the shape that they were. Just like this bow over here. The string on the bow is in a certain position, a rest position. But then if we pull that string back, we deform it. We change it in some way. But it doesn't want to be deformed. It wants to go back to the way that it was. As it's going back to the way that it was, it can potentially move or change other objects, like the arrow that we notched into the bow. Now, it is possible that we change or deform an object so much that it can't ever go back to the way that it was. That means that there's a limit to the elastic potential energy that an object could have. In reality, in theory, two things affect the amount of elastic potential energy an object has. The first is how far do we stretch it? That's the delta x. Again, the magnitude of the displacement. Elastic potential energy can come from stretching something out and maybe making it longer than its original length, but it can also come from compression, making something shorter than its original length. There is no difference in the amount of elastic potential energy, because even if you stretch something or compress it, it still wants to go back to its original condition, meaning that the amount of energy, the amount of change it can cause to other things will not matter. But the other factor that affects it is something that we refer to as the spring constant. As it's described here, how easily a material is changed from its original shape. Some things are very easy to change in their shape, like rubber bands. Rubber bands stretch and no problem. But some things are hard to change their shape. Like if you've ever worked on cars before, your car has big springs attached to it. So when you go over bumps, you don't feel them. Those materials, with how easy they are to stretch them or compress them, we categorize that easiness, quote unquote, to stretch or compress as the spring constant. Materials that have high spring constants are very hard to change. Things like we consider to be solids, tables, chairs, floors, have very high spring constants. They don't want to change from their original shape. But things like rubber bands or chewing gum or something like that might have a very low spring constant. It's much easier to change those things. How hard or easy it is to change them will relate to how much they can change other things as they go back to their original position. Okay, we've now talked about what energy is, but talking about energy in isolation really doesn't do it justice. While we can talk about the energy a material has, what we will find out over the next couple of weeks is that energy is related very closely to this concept called work. So we just went through and talked about energy as the ability to cause a change in the environment, and especially we talked about kinetic energy. It wasn't the only thing we talked about, but it was pretty important. So, work is defined as the transfer of energy between objects. We find out that this energy, this ability to cause change, can be transferred from one object to another. If we go back to this picture here, right, we have the picture of this string on this bow being pulled back, its shape being changed, it gains elastic potential energy. But we discussed, as it does that, it wants to go back to its original condition, straight from the top to the bottom. As it does so, the elastic potential energy that we increased by stretching the string is then transferred to the arrow, but in the form of kinetic energy. That arrow starts moving. So we can find that we can transfer energy between objects. But when we transfer energy between objects, there are two changes. It says an energy of an object will change. It actually should say energy of objects will change, because one object is going to lose energy and one object is going to gain energy. Something's ability to change other stuff will increase, but then some objects' ability to change other things will decrease. How do we know this? Well, let's start with an old equation, right? Here's a Suvat equation. V squared equals U squared plus 2AS. In case you can't remember, V stands for final velocity, U stands for initial velocity, A for acceleration, S displacement. So, first thing we do, subtract U squared from both sides. Then, we kind of pull in something that we learned recently. In this little section right here, we substitute in the expression for acceleration from Newton's second law, F over m, into this expression here, right? We know that acceleration is affected by force and mass, so we can make this adjustment. We can make this substitution. Once we do that, got kind of a complex situation over here, okay? I'm going to multiply both sides by m over 2. That will cancel this 2, cancel this m over here, but it leaves us with m over 2 times the quantity on the other side. Back on the right-hand side, we're left with just f times s. We distribute out m over 2, and we end up with this. While it doesn't look like we wrote it before, this is 1/2 mv squared minus 1/2 mu squared. I took the 1/2 away and I just made it over 2, but it's the same thing. Hopefully you recall that this expression is kinetic energy, or the formula for kinetic energy. So now we find out that we actually have the final kinetic energy minus the initial kinetic energy is equal to F times S. Final minus initial anything is delta. So here we end up with an expression at the bottom. Where the change in kinetic energy is equal to the force we apply to that object times the distance that we moved it. We've just manipulated an equation. It's a situation that we analyzed like this earlier, right? We talked about an object that was moving. This is a kinematics equation or a Suvat equation. But then bringing in dynamics, right? Bringing in the force relationship, we end up with a new expression. It's not anything, or we end up with a new expression to describe a situation that we already have described. So again, we see that energy isn't a new situation. It's just a different way of analyzing things that we already have looked at. So, work depends on two things: force and displacement. How much will the energy change? We multiply the force we've applied to the object by the distance or the displacement that we move that object, and we find out how much work was done. So here we have an expression, this kid pushing this box. If we know how much force he's applying to the object, we know how far it goes, we can figure out how much the energy of that object will change. Now, something to keep in mind. This may not seem intuitive because you may say to yourself, well, wait a second. If this kid just pushes this box down the hallway, it's actually not going to be any faster or slower. It's just in equilibrium. So is he changing the energy of it? This expression, W equals F times S, is related or only applies to a single force. But there may be situations where we have more than one force doing work on an object, or more than one force changing the energy. I think most of you would probably be able to figure out that in this case here, we have a frictional force. It's a dynamic friction force because it's moving. Well, that force is affecting the motion of the object. It's affecting its energy as well. What we look for a lot of times is not just the work by a single force, but the net work, right? The total amount of work that's done by all of the forces. Speaking of, actually, well, before we do that, when we talk about net work, right, really it comes down to, okay, what's all of the forces that may be increasing the energy, what forces are decreasing the energy, and then what's the total sum, right? What do we have, what's our net gain or loss? Here, we have a guy who's applying a force to this box, and it would move because of it. It says, is it work when someone pulls at an angle? And the answer is, yes, but. Here, that force is being applied in this direction. But the box is going to move in this direction. Way back when we started talking about motion in 2 dimensions, we talked about the independence of horizontal and vertical motion. That independence applies throughout, right? Yes, it's independence of motion, but it's also independence of forces, independence of energy as well. So here, we would have to take a look at this and say, okay, because he's not pulling in the direction of movement, this force has components. Only one of those forces, or sorry, only one of those components is in the direction of motion. So is this work? Yes, but the entire amount of force that he's applying is not going to changing the energy of the object. Only one component of it is. So a more accurate depiction of how much work is being done is represented by this equation. F is equal to cosine theta times S, where here the theta is the angle between the force and the motion. The cosine part automatically gets us the component that is applied in the direction. Where is that here? Oh, sorry. Sorry about that. The cosine theta automatically gives us the component of the force parallel to the motion. That's the force that, or the component of the force that's going to actually change its energy. So, what does that mean? Well, energy is scalar, and work is a change in energy, so work is also a scalar quantity. It doesn't have direction. But we will find that that doesn't mean that it can't be negative. Work can actually be positive or negative. But that doesn't relate to the direction of work. It relates to what happens to the energy. Will the energy increase? Will the object have more ability to do damage because of what we've done to it? Or will the energy decrease? Will it have less ability to do damage because of what the force is doing to it. And here is a summary that kind of helps us make sense of that. If the force is quote unquote helping the motion, basically in the same direction, we do positive work and the energy of an object will increase. If we go to this picture here that shows forces being applied to a toy car, here we have an object pulling and then the car is moving in this direction. That force is helping out the motion. It's in the same general direction. Not totally, right? We'd have to get into components and stuff like that, right? So only one component of that force would actually do work, but generally speaking, we have that would help the motion. It would make the car go faster. And if the car goes faster, that means it has more energy. Same thing would be true if we were pushing this car from behind. Yes, the force is being applied to the rear of the car, but it's still in that same direction of motion. And again, we'd have to get into like components and things like that to properly analyze this problem, but there would be one component of the force that's in the same direction as the movement, and that would increase the energy. But if the force is opposing the motion, we're going to do what's called negative work, and the energy is going to decrease. If we go back, oh, wrong way. If we go here, right, this car is trying to move to the right, but there's a string that's holding it back. Again, not completely parallel, so we'd have to do components, but there's one component that is completely opposing the motion. That would slow the car down, and it would decrease its ability to change other stuff. Same thing would be true if we were pushing it from the beginning, right? This car is trying to move to the right. Oop, got to change colors. This car is trying to move to the right. We're pushing it to the left. That would cause it to slow down, and it would have less ability to cause damage than before. But there are certain times that we can apply forces to an object and nothing will happen. First, if we apply a force perpendicular to the motion, that does no work. The energy will not change. If we think about this kid, this kid pushing the box horizontally, there are two forces that are also acting on this box. There's a gravity force this way, and then there's a normal force this way. Those two forces will not change the energy of this box because they're not in the direction of motion. Remember, independence of vertical and horizontal. So if we apply a force perpendicular to the motion, nothing happens. And then again, if we apply a force but there is no motion, right, we know that there's no change in the object. That means no work. And again, that energy will be constant. So, energy, the ability to cause change in other objects or the environment. Work, the transfer of energy, the transfer of that ability from one object to another. And again, like we discussed at the very, very beginning, these are not new situations that we will be analyzing. They are similar situations to what we've discussed up until this point, just another way of analyzing them.